Welcome back to Introductory Electromancy. Last time we talked about the p-n junction and how it comes from the periodic table of the elements. Look at them, all periodic. So I had constructed this experiment where we'd be lighting up a variety of LEDs and then measuring their forward voltage drops. The LEDs all have identical 1 kilo-ohm current limiting resistors. In practice, their difference in voltage drops will mean that the resistors have slightly different voltages across them. Therefore, because of Ohm's law, we'll conduct slightly different currents. But this should be a second-order effect whose size is relatively minimal, so we can safely ignore it for now. Now, we take our exciting battery. I know I'm supposed to use red for positive. I find myself using whatever color happens to be handy. This is exactly how it goes down at manufacturing places, I assume. So, wow, look at beautiful LEDs. Are they not majestic? Now, what's their forward voltage? And importantly, we want to do it by color. So we have red, we have yellow, green, and blue. So VF is the symbol for forward voltage. Let me try and write it more neatly. My apologies, Internet. So I'm going to be measuring that value and writing it down for each of these LEDs. To measure voltage with a multimeter, you set it to DC volts. Do not set it to ohms or you might damage the meter. Do not set it to amps or you might damage the meter. This one is already at the right setting for this, fortunately. So, let's cram some more things in here. And I see I'll need to use my hands to point the meter probes. Let's see. So there is a decimal point on this thing. You can't really see it very well. Now you can sort of see it. So for the red LED, it has a forward voltage of 1.97 volts. 1.97. Then for yellow, 1.95. I see I'm doing great damage to my thesis already. 1.97, 1.95. Green measures at 1.98. And blue that lovely blue LED has a forward voltage of 2.89 volts. So generally, the higher frequency of light an LED produces, the higher its forward voltage should be. Red light has the least energy per photon, then yellow has more, then green has still more, then blue, then after that would be violet and ultraviolet. Below red would be infrared. The reason for this positive trend is because of the semiconductor band gap voltage. Looking back to our p-n diode, this gets rather involved. Different LEDs are made with different materials. Which material you use affects the band gap voltage, that is the difference between an electron that's in the conduction band versus the valence band, which is where the electron falls at where the junction meets. That distance controls how much energy is imparted to the photon. I might come back to this description more later. I feel like I haven't quite done it justice. Other things that I wanted to mention. Diodes are basically one-way valves. They burn 0.7 volts for a regular silicon diode. In the hydraulic analogy, they would be a one-way valve, shockingly enough. Ohm's law is not always written in the form V equals IR. Some people, Feynman, some people like to use E instead of V for electromotive force. They are equally valid. This one is outdated. This is the modern form of Ohm's law. If for whatever reason you are learning from textbooks from the 1950s through 1970s like I was, in addition to learning a lot about beam triodes, you'll probably see E equals IR. Additionally, I wanted to mention a reference text that is of use, dear viewer. I will be adding this to the description under the physical book section. Depending on where you are in electronics, you will already have heard of the 555 timer. It's a timer chip. This chip was designed by a guy named Hans Commonsend. He wrote a book. Which is available on his website for free as a PDF. This book has an excellent description of how the PN junction works and a whole lot of other things. I'll be using it as I go through this description. I'll link it in the description of the video. In any case, Internet, I have hit about my limit. Let me know if I have forgotten anything in the comments. I will attempt to fill in the gaps that I will no doubt inevitably create, attempting to cover the entirety of electrical engineering as a free-form lecture from memory with only the parts I have in arm's reach. Until next time.